All right, we are now live. So welcome everyone and happy Space Week. My name is Lucia and I'm going to be your host for this Hangout. So all week long we've been doing Google Hangouts with astronauts, engineers, astrophysicists, roboticists, scientists, and just so many people who just love space exploring. So thank you for joining us today. Remember, any photos that you take during our Hangouts, you can actually share them on social media using the hashtag #ExploreScience. And at the end of the week, we'll be choosing a few classes to win some National Geographic space books, which is pretty exciting. Now today we have four classes joining us from across, well, right now across America. We're waiting for one more class from Ontario, but we have classes from Maryland, Virginia, and 2 from New Jersey. So welcome everyone. And today we have Dr. Patel with us. She is a Canadian astrophysicist who looks at how planets are formed from stars. But not only Dr. Patel is also a science communicator and works as the Outreach Program Coordinator at the Centre for Planetary Science and Exploration at Western University in London, Ontario. So she loves sharing her passion for planetary science and science in general, and that's why we're all here. So you can take it away, Dr. Patel.
Awesome. Thank you. Hello, everyone. As Lucia mentioned, my name is Parshati. I am going to today talk about, my journey, how I got inspired to study what I'm studying and how I ended up where I am. And then obviously talk about, what in space am I studying and how, these planets form from these disks and stars. So I'm going to turn on the presentation. I'm going to share my screen. All right, so screenshot. Okay, all right. I'm hoping you guys are able to see it.
Yep, looks good.
Okay, awesome. Okay, so I have a quick few presentations, kind of really cool pictures that we're going to look at, and I'm going to be talking over them. So to start with, how did I get inspired to basically do what I'm doing? I actually visited a planetarium when I was really young. So if you have not guessed, I'm from India. I was born and brought up there. And on one of our vacations, family vacations, my parents took me to this city called Mumbai. And they have a huge planetarium there. And I saw the show, and I was looking and I was trying to understand all these stars and how they move. But because I was living in a large city, there was a lot of pollution, and I didn't really see a lot of constellations that they were talking about. So I kept asking my parents all these questions about, where do these planets come from? How do they form? How do the planets form? And my parents' background is biology and business, so they didn't really have answers for me. And I ended up actually, they just bought me books. So I ended up with a stack of books all about astronomy, universe, how planets form, how stars form. And I was at around grade 7 and 8, so kind of almost the age that you guys are at. And something that happened when I got in grade 10, so my aunt who lived here in Canada, she came to know that, I love space and, all that I do is read space books. So she bought me a telescope. It wasn't a big one. It was a small one, just like the one I have in the picture here. But what it allowed me to do was, at my time, gaze at the moon, Saturn, Jupiter, and the moment that the first time I saw Saturn through my own telescope, I had seen it through other telescopes before. But when I saw it, I found it, and then I saw it, it just made me like, this is something I could do for life, and, try to understand how these planets are forming. They're so beautiful. They have so many things that we still don't understand, and that is something I could contribute to. So in grade 10, I decided I wanted to be an astronomer. And I said, now I need to go and study astronomy to know if I could actually do this for a living, because I had the passion of doing it. But whether or not, that's something I would want to do for life only comes, you get to know after you actually take a couple of courses. So I started my education, so I moved to Canada to study astronomy, and my journey started at University of Toronto, where I did my undergrad in astronomy and physics, because I liked physics even before I knew astronomy. So I said, I want to keep something that I'm familiar with, but also it helps to have physics with astronomy, as I was more interested in formation of planets and things like that. So I ended up doing bachelor's in astronomy and physics to have that strong background. And then when I was looking for my master's, I realized that I want to do something that is more concentrated towards what I like. So during my undergrad, I had a chance to basically, do like a thesis when I was doing my undergrad. And that thesis was related to formation of planets and the disks around them. But I wanted to study more. So I came to Western to do my master's. And I got my master's in astronomy and planetary science. So I did a concentration of planetary science because I really wanted to understand all aspects of planetary science. And I'll talk a bit about that when I look at what I'm studying. And obviously, eventually, I did my master's, and I realized I really love this, that I can actually take it 4 more years and do my Ph.D. And so in 2016, I ended up with a Ph.D. in astronomy and planetary science. So again, I decided to take the concentration of planetary science to kind of get a bigger picture idea of what I was doing. So just a quick mention of my education. And the reason why I mention education here is because a lot of people, when they think about space, you want to think A, astronomy, and B, want to be an astronaut. There are 2 things, and there are really wide variety of things you could do. And I'm pretty sure with all the hangouts that you're seeing, there are people who are engineers, there are people who are planetary scientists, geologists, physicists, astronomers, chemists, biologists. They all come together when it comes to studying space. It's one of the most interdisciplinary area that you can work in, and you have a passion for biology, but you can still bring in the space aspect to it, and that's what I love about space. It's very, very interdisciplinary. Anyway, so that's kind of like my background and how I got passionate about it. Let's talk about what in astronomy gives me this really awesome place where I can actually do research. Now, obviously, stars like our sun, they are born from, this giant area called star-forming regions. And they're basically all dust and gas that's lying around. So here's an example of Orion Nebula right here. And all these colors that you see are basically dust, and all these, winds that you feel like you're seeing, they're all gas that's being blown away. And all the dots in here are basically a star. And this is a region where, you have this host amount of dust and gas, the elements that you need for the stars to form. We have a lot of hydrogen. Basically, our sun, what it's doing is it's generating heat and light from burning hydrogen and converting into helium. And all stars do that. That's how they start. And this is where they're born. It's called a stellar nursery as well, in addition to star-forming region. So when you look at these, lovely star-forming regions, what you're seeing are different kinds of stars. So in the previous picture, you saw some stars were really, big, bright blue. Some were very faint, small ones. That's because stars come in different flavors. So they come in different sizes. You could have something like our sun, which is comparatively smaller, as you see. And you could have stars that are very, very big. So maybe, 10, 20, 30 times more massive than our sun. And, for us, sun looks really big, right? But compared to other stars, such as the O and B type stars, our sun is very, very small. And then we have found stars that are way smaller than our sun. So there's this huge range of sizes that come. And with the sizes, something that's very important to realize is that with these sizes comes different temperatures. Because the more massive you are, the more amount of material you are burning, the more amount of energy you are outputting. So their surface temperature can get up to 30,000 degrees. For example, our sun's surface temperature is only around 6,000 degrees. So comparing that, these really big stars are really, really hot. And that means that when planets are forming around them, the processes can be different because you're more massive, you're shedding more material, you have a lot of heat that you are giving out, and then obviously there's a lot of winds that are coming off from the stars. So there are lots of things that come into play when you're talking about forming a planet around these stars. And something to point out is that how do these stars actually form? So in this lovely nebula that I showed you guys before, basically it's all the act of gravity. You have this material being pulled in. Here is a box as an example. All the material is being pulled into one location. And that's when you have all the concentration flowing to this one center. And suddenly you have this, a star with basically a disk of material. So that can be dust and gas. It depends on how much dust there is compared to gas. There's obviously generally in the start more gas than dust. And this is what we called an infant phase or young star. So they're just starting to collect all this material around them. They haven't yet started burning hydrogen in their center, but the material being dumped onto them is so much that it creates this almost like a star-like material right in the center. It's generating a lot of heat and a lot of light. And we like to call them, infant phase or young, very, very young stars. And so I like to study these stars because they make more, they give us this idea of how our solar system came into being if we are going to study these stars. We are certainly past this phase where, we don't have the disk anymore. We have planets and we have the debris, this kind of the asteroids that are left behind. But we don't have what looks like in this picture. So when you get to this phase where there's a lot of dust and gas, the good thing is that we have lots and lots of telescopes. They're looking out to the universe. And what we get is a picture like this. So this was a picture, again, it's the same one that I showed you before, is the Orion Nebula. With the new telescopes, the Hubble telescope for this particular picture, we have actually been able to detect these disks around these stars. So all these pictures that you see right here are actual disks around other stars that we have photographed. So given that, we know in theory this is how it should happen, but with the telescopes, we are actually able to confirm that, this is what we thought and this is what's actually happening. Now, when you look at these disks, they're also called propulwates. That's, short form for protoplanetary disk. And you see they come in wide variety. There are some that are just a disk-like, for example, the one right here, some that have material that's flowing away from them, some that just look, as if there's material, shining away from them, but they're very, very tiny. And you could have all these different kinds, and they all tell us something different about how these planets or how these stars are forming and hence the planets around them. Something that, recently with the new ALMA telescope that has come up, we are able to do is actually photograph an image or actually take an image of a disk. And here is an example. So this is a system called HL Tau or HL Tauri. And this is a disk with a lot of material. And you see there has gaps in the middle. And this is where we think that there might be planets forming. So this is a little bit advanced stage than what I was telling you before, where you just have all this material surrounding the star that's being dumped onto the center. At this point, this disk is a little bit further in its evolution, where you have, basically the disk has settled down a bit. Now you have start forming these, boulders in the disk and eventually into planets. And you start seeing these gaps where these boulders are being formed. And that's the great thing about having, these very technologically advanced telescopes to be able to photograph these. And then obviously we have the artist's conception of how it would look like, right? Generally, most of the pictures that we see in news and media are generally artist's conception. So for example, here's an example. If I were to look at a system that I showed you before, which was an actual picture, this is what I would think how it would look like. There would be lots of, small rocks and some boulders, maybe not a planet, but there's a lot of gas right here. There's a star in the center, and we may have material that's still falling onto the star. But obviously, this kind of relates to what scientifically we think would happen. We are still not at the capacity that we are able to directly photograph these small boulders, but we are getting close. We are going to get there soon. So here is an example. So all the phases I talked about where you have material that's collapsing into right to the center, here is an actual image of that happening. We have a disk that's rotating, and you have basically, the disk of material going around the star, which is now burning hydrogen and helium. You have jets coming out. Here is a real example of that. And then here is another example of the debris disks, which I was talking about and showed you the picture in the last slide. And then given our new technology, we're actually starting to photograph planets. So the last stage, when you move away from, all this dust and gas has dissipated and you don't really see anything, you're just left with planets, which is what our solar system is now. This is what we see. So we have photographed this. It's a system called HR 8799. And all these dots, so B, D, and C, they're 3 different planets. So we are getting to the technology where we are now starting to photograph planets, but it's still very hard. So hopefully in a few decades, we will have the technology to be able to do that. But something that interests me personally in this is actually studying how planets form around massive stars. For young stars, because they're burning less amount of material, they actually live longer compared to these massive stars because they're so massive, they collect all the material, they burn up really, really fast. So their life is short-lived. So the more massive you are, the shorter your lifespan is. An O-type star, they are born and they die so fast that we haven't actually found any planets around O-type stars. What we have, though, found is planets around B-type stars, and they're very, very rare. But it gives us an opportunity to understand what's the difference between forming planets around these very, very low-mass stars who live for millions and millions of more years than the B-type star. Me, because I wanted to study something, that was outside the normal realm. Oh, we'll study, sun-like stars and understand. I wanted to study something that was something that we didn't think about before. And so I decided to, pick B-type stars, very, very young B-type stars to study. And as it says on the slide here, their temperature ranges anywhere from 12,000 to 30,000 on their surface. So these are really, really hot stars. And here's an artist's conception again of how it would look like if we were to be there. And you would see right here closer to the star, you have a region where there doesn't seem to be any dust. It's just gas. And that's because these stars are so hot, 20, 30,000 degrees to the surface, the dust basically evaporates. So closer to the star, you just have gas. Away from the star, you will get regions where you have dust. And I'll show you another picture of, how it would look like. So here is a picture. You have a star. This is not to scale. You have gas very, very close to the star, and then you have gas and dust further away. And this is generally where the planets form, the gas and dust area, further away from the star. That's because there is cooler regions. There, basically material can tumble around and gather more material. Close to the star, you're gonna evaporate, so you're not gonna be able to, hold your form. And so a lot of people study this region where these planets are forming. I was interested in this region, and the reason for that was I said, okay, these disks exist around these massive stars. What kind of effect does this gaseous area have on the stars, but also on how planets around these stars form? Because you can imagine these will be very, very hot compared to this area. So how does that have any effect on planet formation? That's what I wanted to kind of understand, and which I'm still working on. And here's a schematic that I came up with. So I decided that what I'm going to do is collect data, which gives me data about the disk, and then compare it with computational models. And the way I did it was I basically used CFHT, which is a Canada, France, Hawaii telescope in Hawaii. And I collected a lot of observations of these B-type stars. They were very, very young. They're actually called Herbig BE stars, named after George Herbig, who first found them. I would collect the data from there and look for existing data as well. And then I would use a computational model which will generate A, a star. Here's an example. And then B, a disk around it. Using all the basic knowledge of physics that we have about these systems and trying to create disks around them and match the two. So comparing the observations and the computational data, that's what interested me. And what we found was basically that using computational models, we do have a sound understanding of disks around these stars. What we still don't understand is that the formation of these disks around massive stars is way more different than what we think for. So here's an example. If I take the disk, I slice it through and look it through the side, this is how it will look. So bottom picture shows you how a massive star's disk would look like. Certainly these are not to scale. These disks are way more larger than these ones. The top picture basically shows you a disk for a sun-like star. And you see something, first of all, the pure gaseous disk is very, very small compared to stars, which is understandable because massive stars have more temperature, they're high, energy, you have more regions which is going to be gaseous. But then there is something that, was expected from the results that we got, was that you don't need what we call magnetic fields, kind of, gathering all the material and pulling it onto stars. That's generally how sun-like stars form. So we didn't find that you need to have the magnetic fields in order to create all these material or survive. So that was one of our major findings, that we found that massive stars operate differently, disks around them operate differently, and that difference between the two could give us a lot of information on how the planets are forming around them. Continuing work in this region, trying to understand, looking at more stars and getting more data to see, we studied around 4 stars in our database with extensive amount of data, but we now have more data that we have gathered from CFHT that we should be able to add more stars to our database and try to understand how it's a little bit different. Okay, so I talked about these stars and planets and how they form, but how about, I give you like a take-home message to remember. Right? Something to take home is that massive stars, obviously they're way more massive than our sun, very interesting, or equally interesting, I would say, and disks around them have effect based on how the temperature and the size of the star is on the formation of these planets. And we still need to have models that are able to predict what we are seeing in the sky in terms of data. And so we are still not close to resolving all the questions that we have for this, but we at least know that the massive stars have, the formation occurs differently from the low mass stars. And that is a big thing, because we don't want to assume that the way planets around our sun formed, it's not the same way the planets formed around massive stars. So it's good to have variety and kind of understanding of different things that are going on in space. So one last thing I would like to take away, and I know it was mentioned that I'm currently working as an outreach program coordinator, and I love talking to public and students about the awesomeness of space. So during my daytime, what I do is answer the big picture questions. Why are we doing this? What are we learning? How do we want? How are we going to get to Mars? Or are we finding more black holes? And so what I do in my day-to-day life is run outreach events. Go to classrooms, talk to students, talk to the public about the questions they have. I also run a podcast called Western Worlds, and we basically interview a lot of these scientists who are working in space domain, and it's open for public, it's for public to understand what are different aspects of space. And then in addition, we launched Space Camp a couple of years ago. That's something that I was very interested in, getting kids into learning more about this interdisciplinary nature of space. And then last but not the least, obviously my love for astronomy has gone from just being my work to being my hobby. So I do like to do astrophotography when I'm able to get time and when it's warm here in London. So yeah, that's all I have, and I would be more than happy to take questions.
Awesome, thank you. That was great. We can do questions now. We can start with Mrs. McDowell's class. Do you guys have a question you would like to ask?
We do. I have a student who's going to come over and ask. Okay? All right, here we go. All right, you want to ask your question? All right, sit up, move over a little bit more. Right, you can say hello. All right, there you go.
Was your journey to becoming an astrophysicist hard?
So I'm just gonna.
I wouldn't think so.
Okay, got it.
Because oh, sorry. I think it was a longer question.
Okay, I just wanted to make sure you heard it. Was your journey to becoming an astrophysicist hard?
I wouldn't say hard. It's actually a really good question. So a lot of people, think that going to school, like studying for so long, you're going for bachelor's 4 years, 2 years for master's, and then 4 more years for your PhD is going to be hard. I think because I was so passionate about what I wanted to do and what I was doing, I never thought it was hard. I always found it to be challenging to keep me going, that, oh, I have these questions that I want them to be answered. And that just kept me going. I never felt it was hard. I just felt, the challenges that came along helped me to be where I am today. Hope this answers the question. Oh, I don't think we can hear you.
Yeah. Sorry, I muted myself. Host fail. Okay, do we have a question for Mr. Pennington's class?
Yes. Hi, I'm Liv. It's really nice to meet you. The question is, what is your favorite 8th grade science project?
Oh, wow. So as I mentioned, I grew up in India. And back home, education system is very different than what we have here. So we didn't have any hands-on projects that we would work on. However, I don't think I did that in grade 8. I think it was more in grade 6 or 7. I actually participated in a fair, and it might sound really funny, but I made my own volcano from scratch. So that was the only time when I actually had an opportunity to do something hands-on. I didn't actually get to do anything until grade 12. So that was a disappointment. But I feel so lucky for you guys that you guys have that opportunity always to make something hands-on. And now that I do work in an education field, I love doing things hands-on, and I wish I had that opportunity to do that when I was young.
Awesome. Now, do we have a question from Miss Adams' class?
Yes, we do. We kind of have a 2-part question. The first part is, where does the dust and the gas come from, and how do the planets form?
Okay, so that dust and gas is basically all the material. For a star like our sun, it's all the material that has been basically expelled from the death of the star. So you have, once the star dies, you have these explosions, generally called supernovas, and that expels a lot of gas and dust into what we call interstellar medium. So it's basically space-going stars. And dust is what forms the star. So it's, thank those dead stars for us being here. There is a quote like that. And it's actually true. Those dead stars have provided all these elements that we see on Earth, in our solar system, and it's because of those dead stars that we are here. To the second part of the question, which is, how do planets form? There are lots of different theories about how they form. One of the most important one that most of the people agree with is basically you have these dust particles which I showed you in the picture. They basically stick to each other. When they're going around the sun, you are basically bumping into each other and they start sticking to them. So you start with a small dust speck to a small rock to, it's like the snow blowing effect. You start once and you start rolling and then you have a big planet, basically accumulating all the material that comes in your way. And that's how you form a star. Sorry, a planet. So I hope that answers your questions.
Awesome. And then Miss Creech class, do you have a question you'd like to ask?
All right. Okay. A little closer. Okay. When the universe expands, will other planets form or appear?
Good question. So imagine the universe as, if you were going to make a bread, okay? Imagine that to be universe. So you have a small amount of dough that you're putting it into a box, and then it expands. What it does is it's going to basically stretch material out. You're going to have space between stars extend more than actually come together. So if it was coming together, you would have more and more stars form. And the reason for that would be you are then interacting with other galaxies that have gas and dust, and you're forming more stars. But when you're expanding, you're going away from each other. And when you're going away from each other, you're basically, kind of not have the opportunity to interact with the other dust and gas that's around. And so the number of stars and planets that are going to be forming is going to be less. However, that's really, really far in future. So we won't be around to see that. So not to worry about it.
We have time for one more question from every one of the classes. So let's start again with Miss McDowell's class, Mrs. McDowell's class.
Hi, what is astrophotography?
Awesome question. I like that. So, when you guys saw the picture that I showed you, so there are different aspects to astrophotography. So there is a field of photography where you can take pictures of the galaxy in the night sky, which is generally what I do. B, if you have a telescope and a very advanced camera, which is generally a DSLR or higher end DSLR, you can attach that to your telescope and basically take pictures of these nebulas that I was showing, galaxies, planets, interesting field. I haven't dealt with the telescope version yet, which is a higher end of taking pictures, but I like to take star trails. So basically focus my camera to the North Pole and then take around 300 or 400 pictures throughout the night and then create this lovely star trails that you see. And also like to take pictures of the galaxy because it's
Awesome. Now, Mr. Pennington's class, do you guys have another question?
Yep. My name's Taylor, and my question was, what does it take to work at NASA?
Ooh, hi, Taylor. Well, there are lots of different ways you can work at NASA. I do not work at NASA, but you could, work after you do your PhD. And it could be in very many different disciplines. You could be an engineer working, with the robotics section. You could be an astrophysicist working in, solving all these mysteries. And the way to get there is generally a master's or a PhD. After a PhD, you have to do what's called a postdoc, just postdoctoral fellowship. And you have to apply, and it's competitive. And then you have to wait and see if you actually get selected. So, yeah.
Sounds like a big process to get to NASA.
It is.
All right, Miss Adams, do we have another question from you guys?
Yes, Audrey has a question. Would you like to go to space someday?
Oh, wow. I always get this question. I would love to go to space, however, I don't think we are at that, you know, I would love to go to International Space Station, stuff like that. But beyond that, I don't know if I want to go to Mars yet. I would wait maybe 50, 60 years before I would embark on that journey, because I think we're technologically not to be making. Hopefully, well, in the next 10, 20 years, we'll see some of the crew go to Mars, and then I think I would be more confident of going to Mars, but I would love to visit International Space Station someday.
Yeah, that'd be pretty amazing.
Yeah.
And then our final question, Mrs. Creech's class. What do you guys got?
Okay. Have you ever found something that nobody else has?
Oh, wow. Good question. First of all, I love that in your classrooms you have these lovely you know, images at the back of the Saturn, etc. So when I was talking about my research, we actually found that you do not need, so the second last slide I was talking about says, you know, we don't need magnetic fields to see the data that we are seeing. And something that is very strongly favored in the community, or the astrophysical community, is that magnetic fields are required for any kinds of stars you are looking at. And what we were able to, you know, basically find through our models was that you don't actually need them. So that was very exciting. You know, first time you have the Eureka moment. Oh my God, this worked. So yeah, that's my one finding and contribution to astrophysical community.
Thank you so much. This was a really great hangout. I learned a lot about, I think everyone learned a lot about how planets are formed, all about stars. So thank you for taking the time to join us on Space Week. And thank you for everyone for coming in and hanging out with us. So I'll unmute everyone's mics and you guys can all kind of yell goodbye all at the same time and give you a nice big wave.
Okay, goodbye. Thank you.
Bye guys. I hope everyone has a great day. Bye everyone.
Go ahead.